Very good morning, everyone. Thank you for your interest and joining this webinar. I'm Vivek, so I'm going to present you today's session, and we are going to discuss the widely used analysis cases, the response spectrum analysis and PDAL analysis, almost used in every project. We took this topic to discuss it so that the common usage and the integration with the ETABS program for the end user, how we can use it. So we just want to break some myths and then some facts. And obviously, we're going to take you through the features, its integration and usage in ETABS. We hope you will find this both informative and useful. Let's get started. All right. The integration of the code in ETABS, as many of you know that the 1893 code for the seismic as well as 13920 provisions required for tactile requirements for the strength design are integrated in the ETABS. But we'll be discussing that specifically for the response spectrum cases as well as the P delta analysis. So these are the two topics, and let's start with topic number one, response spectrum analysis. The response spectrum analysis, a brief background of it, and in the context of usage in ETABS. So response spectrum analysis is a widely accepted method for incorporating the dynamic effects into the design without the complexity of a time domain simulations. Or in other words, response spectrum analysis is a shortcut from an actual time history analysis that you would be requiring to understand the dynamic properties of the structure and the responses for that. But for a design office requirement, we are interested in the peak responses for the design of the members. So a response spectrum is, at the end of the day, is going to give you only the peak responses. So there are some advantages and limitations one should know, and they are listed here. But basically, it is computationally efficient than a time history analysis. So the resources required will be slightly more than linear static analysis, which we anyway do, and stipulated by the code that you will have a linear static analysis, and along with that, we will perform the response spectrum analysis as well. So it provides the maximum expected response. That's what we are interested in, and it is widely accepted by building codes around the world for the seismic design. So the limitations are we lose the phase information, that is, the signs are lost. That means the directions in which the response is occurring is not available at the end of the day. That is something you should keep in mind. And it is applicable primarily to linear elastic systems. That is also fine because most structures are linear elastic unless we introduce nonlinear devices such as isolators and dampers. Then still it provides a very good start for an analysis to get some numbers. In that also, response spectrum analysis is going to help. So yeah, it is not going to provide time history response, which we are not interested at the design requirement. So requires careful interpretation of results and adherence to code provisions. Yeah, code is also guiding us and how to handle the results. So that is a general response spectrum background. But further, so how we are going to consider this in the analysis is based on the directions. So typically the lateral acceleration, the lateral excitement of the structure is what we are interested in. So most of the structures are weak in lateral than the vertical. So lateral acceleration is the primary concern for overall structural stability and collapse. So it dictates the lateral force resting system design. And vertical acceleration is typically less critical, but must be considered for elements sensitive to vertical motion, such as long span beams, transfer girders, and checking uplift and localized effects. Right. So vertical acceleration should also be considered in these cases. So codes in the ETABS. So what are the features available to perform a response spectrum analysis? So we have two stages. One is the modeling of the structure, from which you will get the stiffness, and then you will be defining the mass source through the loads, and then using them, we will perform a modal analysis. This is stage one, and we will be reviewing the modal analysis results such as natural frequencies, periods, mode shapes, and modal mass participation to ensure 90% participation as per the requirement for most codes, including Indian code. So once it is not achieved, we will have to iterate at this stage and ensure the model results are sufficient to perform a response spectrum analysis. So that will be stage two. And in the stage two, we'll be defining the response spectrum function. It can be a predefined function based on the codes or user defined in case of any user site specific response spectra that you want to use. So program has both the options to select and use, and then you will be defining a load case, which is the actual response spectrum case. In that, we will be specifying few important things. One is the direction and the scale factor. We will discuss about these in a while. And then you will be specifying the modal combination method and directional combination if you're combining more than one direction of loads. And then finally, we perform the analysis, and then review them, and then take it to the design of members. So these are the various stages as well as the definitions that you'll have to make in performing a response spectrum analysis. Now, I will take you through some slides initially, and then I will show it in the model so that it will be much clearer after the presentation slides. So mass source, so stiffness is already coming from the model, so I'm skipping that. So the mass source definition is important for the analysis. So by default, when you define the mass source, so it is under the define menu, mass source. The default definition is element self mass and additional mass. That means whenever you model a member, so the default definition is that its self weight is taken care by the program through the dead load pattern, where you'll have the self weight multiplier 1. So the self weight is always there, and its mass is also available. That will be used. In addition to that, any additional masses directly specified to the objects, point, line, or area. Masses you can also assign to the members, and then you can utilize them. But typically, code requires or simplifies this with the gravity loads, such as dead loads and live loads, and the percentage of the imposed loads we can specify as guided by the code. So for the Indian code, we have 100% dead load and 25% or 50% live load based on the intensity, and you can also modify as needed for the impact loads. So for this, and the mass source, the existing mass source can be modified. Typically, we'll have only one mass source for a structure, and then under the third option, you'll enable this specified load patterns, and then that will enable you to specify the load patterns here. So we typically define the load patterns as dead load, live loads, wind, seismic, snow, etc. All of this will be available. So note this is a load pattern. That means the loads that you will be applying to the structure that will be used. So dead load already carries a self-weight multiplier. So self-weight is also coming into the picture. So no need to enable the self-mass one more time here. So this one option is sufficient. With that default setting, I'm assuming that you're using the default self-weight coming with the member. So that is dead load pattern with the multiplier 1, which is 100%. And then you have live load, is 25%. And then we have the options, how we are going to consider these masses. So by default, include lateral masses will be enabled. And then third item, lump lateral masses at story levels. For building systems, this is quite standard and common that will use these definitions. The masses will be lumped at the story level. In case of industrial structures, you will have to uncheck this to consider masses at different levels, maybe in between stories like mezzanine levels, right, where the masses are modeled. In regular building structures, I'm assuming the RCC and steel, where there are no mezzanines or intermediate levels, that is significantly going to affect your uh, model analysis. We can keep them lumped and simplify things. And then the second item is include vertical mass. So when you want to consider the vertical acceleration and the excitation, then we need to have this enabled for the program to capture the modes in the vertical direction. Right. So that will be the mass source definition. Next one is the modal analysis definition. So we have two types. One is eigen, the other one is Ritz type. You can select one you want. So eigen analysis is a standard classical vibration analysis for the model case. And then you have the option to include the P delta effects or not. That is available through this when the initial P delta and then you specify the number of modes required. Typically, as a thumb rule, we use 3 modes per story for building systems that you can use to start with, and then you can increase it if needed after reviewing the model results in the first iteration. So other settings also available to control the model case. And on the right side, you have the RITS, which is which will be using a load vector that will specify here under the load supplied. So we typically define this as acceleration in X, Y, and Z direction. And then the number of modes you can specify. This will be the standard or the typical definition that we'll make for the model case. And then we perform a model analysis. And the outputs are available both in graphical display as well as the table output. So you can view the mode shape I mean, each mode shape in the graphical, so it will give you a fair idea about the displacements. Through that, you will see the mode shapes which very clearly. But for our interest in finalizing the model results, we will be using the table output. So that is available under the display show tables, and then from the analysis results, structure output, model information. You'll get all these tables, but we will be interested in the model periods and frequencies, as well as the model participating mass ratios. So just example output, typically we'll be ensuring that the model mass participation is 90% for this model case. So that you'll find from this, for each mode is reported here, UX and UI, and then the cumulative sum of that ratio is reported here as well. So you can see them. So about mode 5, you see 97 and 97 in X and Y. But we'll be considering 12 modes, and in the 12th mode, we already see 100%. So this model result is good to use in the response spectrum case. So other requirements such as torsional irregularity checks, which we discussed in the previous webinars, right? For that, you will have to check those requirements as well before proceeding. But for this presentation, we restrict ourselves only to the response spectrum analysis. And then which is to the stage 2, just the response function definition. So we'll be defining 2 functions, right? One is for the lateral and one is for the vertical. So 2 functions. So one for the lateral, we have code-based definitions available in the program. We can simply select them and use it. So one sample is shown here for zone 5, and I and R values can get the spectrum for 5% damping. And then you can define one more function, which will be a user defined for the vertical. There is no inbuilt. It will be a constant spectral acceleration. So we need to define it as a user defined. And I will use the same peak value here, 0.09 for 0 and 10 seconds. So anywhere in that time period range, it will be a constant 0.09 safe G value. With these 2 definitions, we will define the spectrum load cases. So I'm showing one for the lateral, RSA X, and then the other for the vertical as RSA Z. So if you look at the left side for the lateral, you'll be defining this case type response spectrum. And then we define this load input as acceleration in U1 direction. So by default, in ETABS, it is fixed. The joints local axis is oriented with the global axis. So one is oriented in X or parallel to X, and 2 is parallel to Y, and 3 is parallel to Z. So for that orientation, you'll see this is in X direction, and then the function we just defined, and we have the scale factor, which is the initial scale factor, just set to be G. Initial scale factor can be different for different predefined functions. For example, I go back to the function definition. I'm using IS 1893 2016 spectrum function. which has the I, soil type, and R values included in the function itself. If you use 1893/2002, it will not have this, so you'll have to use IG by 2R, and then that will be the initial scale factor when you use the 2002 code spec definition. So we'll have to take care of that uh, in the based on the spectrum function that you're defining. So for 1893/2016, which is the latest, we have all this involved here. We can simply specify the G as a initial scale factor. And then we set the model case and then the model combination method and then the directional combination. It is not needed here because I'm handling this in separate cases. So RSA X, and there'll be another case RSA Y and RSA Z. But if you are defining in a single case, then you can add one more row of data, one or two, for the Y and Z direction here with appropriate factors. And then the SRS's combination type will be utilized. The default is for the model combination is CQC and should be sufficient for most cases. So model damping typically is 5% and is used. And that would be the spectrum load case definition for the lateral. When you come to the vertical, so RSA C, you'll see same, except that the acceleration now it will be in U3 direction. ET is the load name, and then the function will be the one we just defined for vertical, the constant. And as per the IS 1893 code, it is 2/3 of the peak of the lateral. So I'm using this 2/3 here with this G. So that will be the initial scale factor. You can do small expressions within the field itself by multiplying by asterisk 2/3, that will multiply and give you the result in the field itself. You can do this, or you can define this value 0.09 multiplied by 2/3. You can use that value as the definition, and here you can put as G 9806 or 9.81 meter per second square as the initial scale factor. I hope that is clear. And rest of the definitions will be the same. Then once the analysis is performed, you can get the base reactions. It should be noted that program does not automatically enhance the base shear of the dynamic comparing with the static. So it is the user's responsibility to do that. And we will do that by getting out this output, just the base reaction for the static as well as the dynamic cases. You can see this. And the new scale factor will be the existing scale factor multiplied by the ratio of the static divided by dynamic. And code guides you that if it is, the dynamic is lesser than the static, then the enhancement has to be made. That's what this ratio means. I'm assuming that and typed out here as the new scale factor and update this. That is how we do it. And the next thing is the output. And certain things we should know how the program handles the response spectrum analysis results. As I told in the beginning, the responses are absolute maximum values, so there are no signs. Then program internally treats such cases, including response spectrum, time history, multi-valued combinations. The program automatically produces multiple sub-combinations using maxima minima permutations of interacting quantities, right? And these are the quantities P, Mx, and My, and you'll see this in the design force output. So when you see, let's say, a decon 3 load combination, which is by default dead load 1.2 times, live load 1.2 times, and seismic 1.2 times. So if you take this particular combination, you will find under the design force, you will see decon 3 underscore 1 to decon 3 underscore 8 for each member, and then there will be combinations following this sign convention to get this. So separate combinations with the negative factors for response spectrum cases are not required. So we see people defining one more spectrum case with negative, which is unnecessary. It's what we're point I'm trying to make here. Let me show you. I want to switch to a model. And this is where the definitions are under the define mass source. Load cases. So for this model, I used RITS, and I'm using 40 modes. So 10-story RCC symmetric building, typical floors. Let's run this. Once analysis is complete, you can get the deformed shape for reviewing the mode shapes. So 1 and 2 are translational. The third one is torsional. So I'm looking at the model participating mass ratios. Earlier, this one will be for the actual model. For the 40 modes, you can see 100% in X, Y, and even in vertical also. So when you're performing the vertical acceleration, uh, uh, it should be noted that we'll be typically using membrane type of flow slabs. So the masses are actually distributed, but membrane, it will transfer loads to the frames. So the mass excitation should happen at the floor also. So you need to model the flows as shell in this case to get the participating mass ratios, depending on the project. We'll have to review this. And then the output will be picking up an interior frame, and you see a moment diagram, and you will see all the values are positive, right? So that's why the program uses the sub combinations, which I explained a while ago, but leaving no additional efforts for the user to handle these. So all of this are taken care automatically, integrated well, both in analysis as well as in the design. So we are not interested in the design, but just for the sake of showing you that output and performing the member design. Right. Let's pick any one of the column. And then if I go to the display, show tables, and then there will be under the design forces. This will be available only after the design is performed. And then you can select. I've used the default combinations, and you will see the sub combinations when it is displaying that. I pick up any one. I will select one station location 0 as for showing this 8 combinations, and you can see the p values, the moment, and other forces. Right, to obtain the maxima and minima, and absolute maxima will be used, but internally this is handled in the program for the design of the members. And one another important point is the deflections that you obtain from the spectrum cases. So the deflected configuration of a structure subjected to a load combination, which includes a response spectrum load case, is meaningless since displacement sign convention is lost during modal combination. Right. So what you can say is if your building is having the predominant mode 1 of the translation, then still you can use this output. But in general, theoretically, the signs are lost, you cannot use it. So in some situations, when you want to check for these serviceability criteria, then the best way is to convert this linear static the response spectrum cases to the linear static cases and check for this. So one option which we usually recommend is to perform the response spectrum analysis from the story shear diagram or from the table output, and you can get the story forces and define a user-defined load pattern for the seismic and apply these forces as diaphragm forces and perform the analysis and check for all the serviceability requirements. That you can do easily. It is also useful in transferring such forces to the foundation design also. All right. That's the discussion we want to make for this response spectrum analysis. Now let's switch to the second topic of the day, which is the P-delta analysis. So P-delta analysis we have been doing for quite a long, and it is a well-known feature of ETABS that you'll be doing an initial P-delta analysis, right? But in this presentation, I will introduce you to the other ways of handling the P-delta analysis. So the P-delta analysis and the options in ETABS. So basically, the P-delta analysis captures the softening effect of compression and the stiffening effect of the tension, which is integrated in the analysis itself. So you don't have to specially perform any analysis for this. Just need to enable the required data, which you will see, and then the stiffness matrix will be modified for this geometric nonlinearity case, which is a function of load and the length of the member. So we have been doing this single P-delta analysis under gravity and sustained loads can be used to modify the stiffness of the nonlinear, for the linear load cases, which can later be superimposed. So very simplest way, and we have been doing this for the IS 1893 code, where the factors and load combinations are not explicitly explained in the code. So our recommendation was to use the sustained loads, which are the dead loads and live loads. And we are combining this with the lateral load, and with dead load and live load, the combination load factor would be 1.2 as per the Indian code. So we recommended this 1.2 dead load and 1.2 live load as the load for the P-delta case, right? So alternatively, you can do this, just each combination of loads can be analyzed for full nonlinear P-delta effects. So program has the capability of performing nonlinear static analysis. So you can utilize that and define the loads for each combination and converting it to a load case and use it. So these are the two approaches, the latter being the actual full nonlinear P-delta effects, while the initial P-delta analysis, which you've been doing, is also useful, and the results will be very much comparable. And first one, which is single P-delta analysis, is very convenient to define and use. All right, and then this is integrated into the analysis and design seamlessly. That's what I initially told. And then the second order analysis, how these are explained in the code. So we have been using the indirect approach through the design, like by calculating the effective length factors using the Woods chart given in the IS 456. Right, it states that in the absence of more exact analysis, right, when you do hand calculation and all, we will not be able to do this. So we generally use the approximate effective length factor methods for sway and non-sway. So the classifications, all that is utilized in the design stage, not in the analysis. So your primary analysis is not capturing the second order effects. Now, when you do the P-delta analysis, these are captured. And for the analysis, code also guides you what is the stiffness to use from the IS 456. You will have this relative stiffness, either it can be gross, transformed, or cracked section, but it should be consistent throughout the analysis. And when 1893 is used, then it is giving you the 6.431, this, these factors, which will typically modify the I value that dictates the stiffness of the members. 70% for the columns, 35% for the beams. And the new code for the tall buildings is also giving you this property, but our scope would be restricted only to the definitions and various approaches. So we have the factors input from the code. So in the ETABS, we will be doing this default P delta, which is also called the initial P delta analysis. This is what we'll be doing under the define. You'll be defining the P delta loads, and then all the linear static cases will start from the stiffness at the end of this P delta case. This is kind of automated in the program. This is what we've been doing for IS 1893 code. And then there is a second option that instead of the default P delta, you define a P delta case and then use it as a starting stiffness for any other load case. So this one would be completely under manual control. You'll have to mention this stiffness for the linear load cases. Only one load case will be nonlinear in both of these. That would be the P delta case. Rest are all will be linear cases. So when it is linear, then it is convenient to combine them in the load combinations. That is the benefit you are going to get, the design point of view. And the third approach is the nonlinear case definition for the P delta, or in other words, this is the full P delta analysis. So this one requires a simple conversion of the load combinations, all the design load combinations into individual nonlinear static cases. So this also program as automated feature under the load combinations, you can do this conversion. You just need to press the button to convert, and then the rest is taken care till the design. So if you review the usual P delta that we do, we have this definition under the define. You'll be defining it as iterative based on loads, and the dead loads and live loads are included here. That's the definition. And then when you look into any load case, especially the lateral, you'll see the use preset P delta settings will be based on this definition. You don't have to do anything else beyond this definition. Initial, set the P delta options. That's it. It is done, and you can perform the analysis and then go ahead with the design. That is what we've been doing for most cases. So when there is a situation that you'll have to consider a different combination other than the sustained loads, for example, the lateral loads you want to consider, which is given in the tall building code, right? Then you may use the second option, that is the user P delta. So what we will do in this case, we will turn off the defined previous one. So to avoid any confusions, we'll simply turn this off by setting it to none, right? And then you will define a P delta case that will be a nonlinear static, and it will be a similar definition like previous one. And here you can add all the loads that you want in this. Now you can extend this to include EQX or EQY load pattern. But note, each P delta that you define here should have only one lateral load at a time. So for X and Y, typically we'll define these two orthogonal directions. You will have two P delta in user cases. And then the respective lateral load case should start using this particular, which you'll be specifying through this, which I'm showing in this slide, that I'm defining a linear static case for the lateral load. So it is a lateral load, seismic load, let's assume this. And then it is a linear static, but this time it is using the nonlinear case, the previously defined P delta user, this one. And then this can be EQX, for example, right? Similarly, you can define one more P delta initial for the Y direction and include the lateral load of Y or the factors specified in the tall bending code. You can do that for n number of initial P delta and then respective linear cases. So in both of these approaches, the load cases, the lateral load cases remain linear static. That is a big advantage. Yeah. Now the third option, just a full P delta, convert all design load combinations into nonlinear static cases. So you can convert user defined or the default combinations, and then press this convert combos into nonlinear cases. That's it. So what program will do after this? And note again here also, you don't need this preset P delta, which under the define, we'll set it to none. So each load combination will be a new load case automatically added, and it will have all the information from that load combination, which is the load factors and the loads. And importantly, here you need to notice that it would be a nonlinear static, and then the geometric nonlinearity will be enabled for the P delta. So nothing you'll have to do, just reviewing this to understand what it happens after that, pressing that convert button. And then if you look into the decon S3, which has been converted, now it will be replaced with that nonlinear case with a scale factor 1, because the user load factors are already considered in the load case definition itself. Right. Now, just to demonstrate this, only the approaches is you have a cantilever column with a gravity load and a lateral load applied, and comparing all the three methods here, which is giving the same deformation. And the last one is varying in the second or third digit after the decimal, which is insignificant. Right. I want to show you that. Then you have this model. This is the initial P delta. We usually do P delta options based on iterate. I'll put into none just to show you the difference. So how the P delta effects are happening. So without P delta, we are going to run the analysis. So only the linear static cases, no P delta. We check the deflections for the lateral. So it is 10.083. And then if you look at the load combination, which I have defined for standard dead load 1.2, live load 1.2, and the lateral 1.2. P delta is turned off for this. The other two are for nonlinear. We'll come back to that. So we are focusing only on the first one without P delta. And if I look at the moment diagram for this, and you can see 180 is the moment at the column base. I unlock this, and I'm going to enable the P delta options with iterative based on loads, these sustained loads, and then run the analysis again. Now, if I check the lateral load case, now we can see 10.876 is the displacement at the top, and then the moment diagram for the same combination, 191.82 kilonewton meters from 180 without P delta. All right. Now let us enable the other two for the comparison. One is setting up an initial P delta similar to this one. Make it run, and the lateral load, which is using this P delta. So the definitions are the same. Let's run now. If we check the deformation for this case, lateral using user P delta, I will see exactly the same value. And we have one more window that would show the combination with a user P delta and the lateral loads. You can see both are identical. Right. And the last approach is this. We have defined a combination, lateral nonlinear P delta. And then we converted this into nonlinear case, which I will show you here. Lateral nonlinear P delta, linear static. And here I have used, imagine that any regular combination with all these load and load factors, including the lateral loads. So this is the definition. And it will have the P delta. Right. Now we are going to run this case. Here, if you switch to this load combination, and you can see 191.75. This is 191.82. Small difference, but still the simplified approach is on the right side. Either it is from initial P delta or the user-defined initial P delta. Both are initial P delta analysis. On the left side, just the full P delta. The difference is the computational effort it requires in this case, but it is very much simple with the ETABS features that is completely automated here for you. So these are the results in the load combination definitions I just showed you. So thank you. That's all I wanted to present to you.
Thank you so much for such a great presentation, Vivek sir. There are some questions in the chat if you could just go through some of them. And
Okay.
the rest of the question, I'll just get back to you after Vivek sir has answered some of them. So Vivek sir, you can continue. I'll meanwhile share my screen for you, everyone. It has all the contact details and it has the personal email ID also. You can drop all of your queries on the email ID and we'll answer them right after the webinar, latest by Monday. So Vivek sir, you can start.
Yeah, I'm just looking at the questions. There are some general queries related to the modeling and other things. I will restrict myself only to this topic. Yeah, right. So there is a question, how P delta and model analysis to be conducted together as one in linear and another non-linear. So what happens is the model analysis requires a stiffness. So that stiffness would be from the P delta, and beyond that, it is the model result. So it will be linear only. So that is the idea of initial P delta analysis. So that when it gives the stiffness to start for all the linear cases. So P delta itself is a nonlinear case. Yeah. Yeah. While defining response spectrum in vertical direction, why we have considered the maximum acceleration for the whole time region 0 to 10 seconds. Yeah, the code 1893 is giving you the flat or the peak one and two-thirds of it. That's what it is. So that's why we took only the peak value that is acting throughout it. But typically, the time period for the vertical axis will be very small compared to the lateral. And but code recommends to use this peak value in any time period region. So that's the reason. So we already have 100, 30, 30 to include lateral effects. So do we use SRSs in direction combination within RSS definition? Um, yeah, actually, it is automated, but if you have specifying this, then it is not needed. So I don't know how you're defining this in the load combination. You're using 30-30. That is the usual approach people do. But within the load case definition, you include all this, and then program will also implement this ratio, specified ratio for that. And why are we using CQC for model combination? I think and SRS is for directional combination. Yeah, we have to specify the model combination method, which is by default CQC. SRS is also available for model combination, but it will be conservative. So CQC will have the correlation of the successive modes. If it is very close, then correction factors will be applied. And essentially, when they are separated, then uh, it will be SRSS automatically. So, but CQC, because the computational effort is not needed by the user. So program is taking care of it. So you can go with the CQC for the model combination. And SRS is directional combinations required only when you're combining more than one loads in the load supplied. How to get 0.09? In the slide I showed, it was the peak value of the lateral response spectrum we defined. I use that for the vertical. Is there a need for initial scale factor? If we are giving scale factor at the later stage, yes, we might need uh, unscaled for serviceability checks. Then you might need that. For dynamic eccentricity, how you suggest apply scale factor? I think it will be the same because the scale factor is only comparing the base shear, nothing else. So base shear has to be matched as per the code. If RS base shear is higher than the static, um, this may happen for stiffer buildings, yes, you have to use uh, the actual base shear, which is higher than the static. You cannot reduce it. How to scale Z component? Code suggests that same ratio we obtained after the initial analysis, right, for the scaling with the horizontal base shear. That ratio, let's say it is 1.5 times or 2 times, either in X or Y, whichever is greater, that should be the scaling for the Z direction. Now, yeah, if we are combining the other load cases, you don't have to define the orthogonal effect in the load combination. Yes, because the loads are already acting. Yeah, do we always get vertical mass participation more than 90%? That's why I recommended that you need to uh, use shells for the floors, and then the 90% will be achieved easily. Yeah, but sometimes you will have to increase the number of modes also. So use Ritz vector so that it will converge very faster. It requires very less number of modes. How is it possible to identify tension in vertical members using the response spectrum analysis? Yeah, you will have to see the design force output I just showed you in the presentation. So one of them will show you a positive value, then it is in tension. So otherwise, since this is combination, because it is not uh, viewed in isolation, then you'll have to see the combination, design combination output for such effects, whether it is really going into tension or not. Yeah, it is better to obtain the horizontal displacement using static analysis. Uh, uh, Response spectrum analysis you will have to perform for the member design because the force distribution will be different from the static. That's why I recommended to convert this response spectrum into static for this purpose related to the serviceability checks. So P delta based on loads is a recommended one. Based on mass is for simple, simplified structures like columns or something like that, that masses are lumped completely. But we have a distributed mass system, so we recommend using the P delta based on loads, iterative. Yeah. Okay. Do we have to do P delta analysis for every structure we design, or is there specific conditions to be met before using the analysis? No, you can do P delta analysis for all the structures. Maybe very small, low-rise buildings, you might you can ignore this, but in general, we recommend using P delta analysis for all the structures. So, which among the two earlier cases of P delta is more recommended? Okay. So, when you want to take control on the load factors combined with the lateral loads as the P delta loads, then you will have to use the user-defined initial P delta cases. Or our recommendation is simply convert all the load combinations to nonlinear static cases, as I showed, as a third option. That is the simplest way to ensure all the load combinations are designed for the P delta effects in respective directions with the loads. So second option is a bit involving because you'll have to define multiple initial P delta for wind and then for seismic, and then use it correctly in the respective cases. So the responsibility will be in the hands of the users to ensure all these are chained properly. Yeah. What is the significance of load application set to full load in load case data? In the nonlinear static load case definitions, we have the control to apply the load incrementally or displacement controlled. So in that, by default, it is a full load. That's what we have been using this for this requirement. But sometimes you need to apply a displacement control load, then you can set this to displacement control. That's the requirement. The presentation will be shared. There are questions as initially told by Mr. Lakshay that these presentations will be available shortly. I think the example I showed you for the P delta effects in a single cantilever column, it showed the difference in the effect of the axial force at the tip of the column, right? The without the P delta, it was only 180, and then with P delta, it is 191. as the base moment. So that tells the significance of the P delta analysis, right? So that's the reason we are doing this in a framed structure also. In a real structure also, uh, it will capture this effect nicely. So I hope our presentation was helpful to you, and we'll meet you in another presentation very soon. Thank you all.